All right. Recall from last time that we saw y equals c over x was a one-parameter family of solutions to the differential equation xy prime plus y equals 0. So let's quickly get a look at this in Desmos. Okay, so what you can see here in Desmos are just a bunch of individual particular solutions for different c values, c ranging from -3 to +3, including the solution y equals 0, which occurs, of course, when c is equal to 0, giving that horizontal line right through the origin there. So we're going to make a couple of observations here. One of them is noticing that the curves do not seem to intersect each other. They're not crossing each other, are they? Now, what this seems to suggest is that if we pick an arbitrary point in the plane, for example, the point 4, 3, okay, there it is, then we ought to be able to find a c value specifically associated with a particular solution that will go through 4, 3, and there will be only one such solution that will go through 4, 3, because the curves don't intersect. To see things a little more clearly, I've turned all of the particular solutions red, except for the point we're interested in, which is 4, 3, and our one-parameter family with the slider c, which is going to show up in black. And you can see that as we slide the values of c around, the graph reflects a particular solution associated with that constant c value. So this would be the graph -8 over x, because our c value is -8. And what we're after is we project that with a particular c value, we will get the graph that crosses right through 4, 3, and it looks like right about there. There we are. So when c is equal to 12, the graph y equals 12 over x is the unique particular solution to this differential equation that intersects 4, 3. So from this analysis, we can make two projections about the behavior of solutions to differential equations. One, it doesn't seem like they intersect. And two, it seems like no matter where we place a point on the plane, we'll be able to find a c value that intersects it, which means that the entire family of general solutions kind of covers the whole plane, right? There's an infinite number of lines, and you could sort of paint everything by just laying down all the curves, right? Now, both of those facts are mostly true, and we're going to establish that with something called the existence and uniqueness theorem toward the end of this section. So let's kind of work out analytically what we just did. What we just did was we solved something called an initial value problem. All right. When we were playing with Desmos, we had this up. We wanted to solve that differential equation subject to the condition y of 4 equals 3. Right? So this means passing through the point 4, 3. Well, we know that y equals c over x is the general solution to this differential equation. So what we're going to do is plug in the initial condition and solve for c. Here's the general solution. Okay, we plug in the initial condition, which is y of 4 equals 3. So passing through the point 4, 3, which means y is 3, x is 4. And if we solve for c, we see that c is indeed 3 times 4, which is
calculating
12. So the particular solution is y equals 12 over x. All right, and as it turns out, that is the unique solution to this differential equation subject to this initial value. All right, now this is called an initial value problem. Okay, let's define an initial value problem. So an nth order initial value problem, which is commonly abbreviated IVP, is an nth order differential equation. So I'll just write one in normal form here. Normal form, recall, that's where the nth order derivative is isolated, which means that everything on the right will just be a jumble of x, and then all the lower derivatives, so y, y prime, y double prime, down to the n minus 1th derivative. Okay. And this differential equation is subject to n initial conditions, specifically of the form where you are given an initial value for y, an initial value for y prime, an initial value for y double prime, all the way down to an initial value for the nth derivative. All right, so that's pretty much it. The one thing that's important that you recognize is that the x-coordinate for the n initial conditions are all the same. The y-coordinate, of course, will depend on the order of the derivative, which is why they have different subscripts here. In the last example, we only had one initial condition because it was a first-order differential equation. All right, so at its heart, an initial value problem is just a differential equation and n conditions according to the order. So we have a first-order differential equation here and one condition. Now, of course, let me just remind you of something you already know, which is we don't actually know how to solve differential equations yet. That's going to come in the next chapter. So for all of the exercises in chapter 1, we're just going to be magically handed a solution and told, here, this is the one parameter family, so just find the particular solution that you need. So of course we're just going to plug t equal -1 and y equal 1 into the family of solutions, or the general solution. So that's y equals c1 e to the t, and with y being 1 and t being -1, we now just have to solve for c1. So, of course, we can see that c1 is equal to e. So the particular solution is y equals e times e to the t, which of course is better written e to the t plus 1. All right, so here are a few different particular solutions generated from that family of solutions. So these are just y equals some coefficient times e to the t, including y equals 0. And again, I want to just stress that these curves do not intersect. So even if you zoom in, they're not actually going to touch each other, right? So the point we were interested in was -1, 1. Okay, there it is. And we found the solution y equals e raised to the t plus 1. And you can see it goes right through our point. So we win. Let's do a follow-up. What is the largest interval of definition? Well, the exponential function doesn't have any singularities, so I would go as far to say it's just -infinity to positive infinity, or all real numbers. Okay, in this example, same imperative as the last one, just different differential equation, different proposed solution, and different initial condition. So we are handed a one-parameter family of solutions. We could, of course, verify that. We know how to do that. We're not going to. And we'll solve the initial value problem. So all we do is we plug in the given initial value and solve for C. Very good. So 1/2 is equal to 1 over -2 squared plus C. All right, well, if we cross multiply that, we'll get that 4 plus C is equal to 2. And therefore, C is equal to -2. So therefore, our particular solution is y equals 1 over x squared minus 2. All right, now let's find, again, the interval of definition, or the largest interval of definition that's available to us. Now this one's going to be a little more interesting. Okay, so let's note that the domain of this function here as a function, right? So as a pre-calculus question where it's just write down the domain of this function, we know that it's all real numbers except plus or minus the square root of 2, right? So the domain of this guy is all real numbers except for plus or minus rad 2. So I'm writing it as intervals because we really want to pull out an interval here for the interval of definition. Now, the interval of definition, you can't just pick any one of those that you want, okay? The interval of definition that you choose to associate with your particular solution must include the initial value. So the x value that was given was -2. All right, well that means that we must choose this interval here, -infinity to -rad 2. All right. Okay, until now, we were just solving first order initial value problems, but now we have a second order initial value problems, and it has a 2-parameter family.
This is getting out of hand.
So we have 2 initial conditions, and note that they both share the same x value. So first of all, let's plug in x equal pi over 8 and y equals 0 into the family. So here was the solution as it was given. Now let's replace y with 0 and x with pi over 8. So we have rad 2 over 2 c1 plus rad 2 over 2 c2 plus 1. Okay, now we are going to need another equation in order to conclusively determine the values of c1 and c2. Of course, we haven't used the other initial condition, so let's throw that in. But we're going to need the derivative for that. So we should find y prime, then we'll plug in its initial condition. Okay, so here's y again. So y prime is the derivative of that. And now we will plug in x equal pi over 8 and y prime equals rad 2. Okay, so we have quite a bit of cancellation. The 2's here both all cancel. And the rad 2's also all cancel. So we get something nice. 1 is equal to c1 minus c2. Okay, so we just have to solve this system of equations for both C1 and C2, and we're off and running. Okay, so first of all, let's take a look at, let's call this first equation, equation 1, second equation, equation 2, and let's actually clean up equation 1 a little bit. We can see that with equation 1, we have negative 1 is equal to rad 2 over 2 C1 plus rad 2 over 2 C2. And in fact, if we just multiply both sides by rad 2, then we're going to have negative rad 2 is equal to C1 plus C2. All right. And if we put right underneath it the other equation, then we can actually solve this one by elimination. If we just add those two equations, then we're going to get 1 minus rad 2 is equal to 2C1, and therefore C1 is equal to 1 minus rad 2 over 2. So hopping over to equation 2 at this point, knowing our value of C1, we can say that 1 is equal to, well, here's the original equation 2, and now we replace C1. So we can see what C2 is. C2 is 1 minus rad 2 over 2 minus 1. Okay. Which would be negative 1 minus rad 2 all over 2. Or negative 1 plus root 2 over 2. So if we recall our general solution, which was that, and we now know C1 and C2 as they pertain to the particular solution, we can write out the particular solution. C1 plus C2 All right, and that lovely thing is our final answer. Now, what about its interval of definition? Well, sine and cosine, those have domains of all real numbers. They're differentiable everywhere. So as odd as this particular solution is, it does have a max interval of definition of all real numbers. Okay, and here's its graph on Desmos. Now, of course, that doesn't confirm that it's really the solution to that differential equation, but we can see if it goes through the point pi over 8, 0, and it appears to right there. So it satisfies that first initial value. The second initial value says that the derivative there is the square root of 2. So square root of 2 is about 1.4, so you could convince me that that particular dot has a slope of 1.4. Without working out its whole tangent line, we could just take an arbitrary graph of a straight line whose slope is exactly rad 2, and we don't know its y-intercept, so let's just go plus b. We'll add a slider for b, and now we can move it around, and let's see if it, yeah, look at that. It seems like it's exactly tangent to the point that we're interested in. Okay, let's bring the conversation toward existence and uniqueness of solutions. Right. So far, when we solve these particular equations, or in the last case, a system of equations, of course, it produced a single solution, right? That's not always going to happen. Some initial value problems may have multiple solutions. All right, so for example, let's suppose we're asked to solve this initial value problem. We're told the derivative of y with respect to x is equal to x times the square root of y. And we're also told that the solution must go through the origin. Okay. Well, one could easily verify that y equals 0 is a solution to that. Okay, the derivative dy dx is of course 0, and 0 is equal to x times the square root of 0, 0 on all sides, so yeah, that one works. But also, y equals x to the 4 over 16. Okay, this one we could easily check without much work. We can see that in this case dy dx, the derivative of that would be 4x cubed over 16, or x cubed over 4. All right, but if you take our y and you just insert it into the differential equation here, you're going to get the square root of y, which is x squared over 4, multiplied by x is x cubed over 4. So it is a solution to the differential equation. And just like y equals 0, they both satisfy the condition y of 0 is 0. In fact, these two curves intersect there, if you were to graph them. So what's the deal? We have a theorem called the existence and the uniqueness theorem. And it's going to tell us exactly what the conditions are for which we can guarantee that there is a solution and that it is unique. All right, so the existence and uniqueness theorem for first order IVPs. So let's say we have an initial value problem. So we have a differential equation written in normal form, and it's subject to the initial condition y of x naught equals y naught. Okay, now the next sentence I'm going to write is going to involve a partial derivative, which I know isn't technically covered in a prerequisite for this course, but it's a very simple application of the partial derivative, and I'm going to explain how to use it right after we finish this sentence. So the sentence is the following. If the right-hand side of normal form, so if that jumble of x and y is on the right, and the partial derivative of f with respect to y are both continuous in a neighborhood of the initial point x naught, y naught, then there is a unique solution y of x defined on an interval containing x naught. Okay, so that's the existence of the uniqueness theorem. Okay, now how do we take that partial derivative? What does that really mean? So I'm going to take a quick detour and just teach you really fast what that partial derivative means. Well, suppose we have the multivariable function fxy is equal to, say, x squared plus y squared plus 5xy. Then the partial derivative of that function with respect to any of the variables, but here we only care about the partial with respect to y, is just the derivative of that function with respect to y. Okay, now all the variables in there are on equal footing. It's not like y is the dependent and x is the independent. We don't care about that in this context. So we are taking the derivative with respect to y, which means every other variable in there is a constant relative to our derivative. So we encounter the x squared. And I know your instinct is to say, oh, 2x, right? Derivative of x squared. But no, x squared is a constant. We're only taking the derivative with respect to y. So the x squared's gone. Okay. The next thing we encounter is y squared. Okay, that's just 2y plus. So what do you think the derivative with respect to y of 5xy is? Well, if it were just 5y, then the answer would be 5. But it's 5xy. Yeah, but the x doesn't matter. It's just a constant relative to y. So this is just the coefficient of 5xy, which is 5x. So that's the partial derivative of f with respect to y. Okay, it's as simple as that. It's as simple as treat every letter as a constant and only take your derivative with respect to y. So incidentally, if we had a differential equation and it were written in normal form here, and its right-hand side were that particular f, and we just showed that the partial of f with respect to y is 2y plus 5x, which is continuous everywhere, right? That's linear. That means that this particular differential equation will have a unique solution for every point in the xy plane. Okay, what we're doing here is we're taking a differential equation, first order of course, and using the existence and the uniqueness theorem, we're going to determine where in the xy plane we have points that, were we to build an initial value problem using those points, we'd be able to guarantee that a unique solution existed to that particular initial value problem. So, all right, we know from the existence and uniqueness theorem that we need to write the differential equation in normal form, which this guy is already in, which means there's our f of xy. Now, f of xy itself has to be continuous, and the partial of f with respect to y has to be continuous. Okay, now this one is continuous. It's just no problem there. So f of xy is continuous on the entire xy plane. Symbolically, by the way, the xy plane is like the real numbers squared. So, all right, but what about the first partial of f with respect to y? So 1/3 y to the negative 2/3. So we could write that as, say, 1/3 y to the 2/3. And we can see, well, everything's fine there, except when y is equal to 0. Okay, so visually, what would that look like? That would be everywhere except where y is equal to 0. So that means that we're okay up here, and we're okay down there. So how would we describe this? Well, why don't we just say half planes defined by either y is less than 0 or y is greater than 0. How about this old friend of ours? Okay, same imperative. So the first thing we should do is write it in normal form. Okay, so y prime is going to be negative y over x. And we can see that our f of xy is negative y over x. All right, so let's first stipulate where that's continuous. So f of xy is continuous everywhere except where x is 0. So we have to rule out the x equals 0 situation. Now we'll take its derivative with respect to y. Okay. We can see that treating x as a constant, you don't need the quotient rule. This is just going to be negative 1 over x. And in fact, that has the same restriction as the continuity of just fxy does, right? That's going to be continuous everywhere except where x equals 0. So we just rule out wherever x equals 0, so that's the right and left half planes that are the good guys. So the visualization of that would be something like this. So we're just going to rule out everywhere x is 0, and everywhere else is a good guy. So we're talking about the half planes defined by x is less than 0 or x is greater than 0. And we've We've played with this differential equation a lot. It was the first one we talked about in this lecture, and the point 43 is in the right half plane, and that's why we were able to find a unique solution. But had we chosen a point that's not in the right half plane, had we chosen a point that was along the y-axis where x equals 0, then we are not guaranteed that a solution exists, or if there is a solution, we're not guaranteed that it's unique. All right, let's do the same thing to this one. So we can see here that our f of xy, this is already in normal form. So we know that fxy is defined when the product xy is greater than or equal to 0. And it'll be continuous everywhere it's defined. So we can say that fxy is continuous where xy is greater than or equal to 0. Okay, well, where is that? Well, if you think about it, that's just the first and the third quadrants. Right, so either x and y are both positive or x and y are both negative for this to be satisfied. All right, now let's take the first derivative with respect to y. Okay, the derivative of the square root of stuff is 1 over 2 times the square root of that stuff. And now we'll multiply using the chain rule by the derivative of xy, which is just x. So that's like x over 2 rad xy. So where's that continuous? Well, pretty much the same places, except now we're not allowed to have x times y equals 0. So strictly greater than 0. That's still quadrant 1 and 3. So, and that is our final answer. So the picture would be that part, and I'm trying to be careful not to include the axes, and that part. So there's a good guy, there's a good guy. All right, so in fact, it's easy just to say that. Our answer here would be first and third quadrant. All right, so for our last example, we're given actually 2 initial value problems. We have the same differential equation and then just 2 separate initial conditions. And we're asked to determine whether or not each initial value problem has a unique solution. So most of the work we're going to do before we even look at the A or B part here. So we're first going to just take this differential equation and first write it in normal form. And then we'll take a look at that fxy and its partial with respect to y and see what we can figure out. So in normal form, we have isolating that first derivative. We have y prime is equal to y plus x divided by y minus x. Okay, so there's our fxy. And we can see that fxy is discontinuous when x equals y. So right away, looking at B, we can actually see that x and y are the same number, so fxy will be discontinuous there, which means B will not provide a unique solution. All right, if we were to visualize this, and I'm not going to, we would be considering the entire xy plane, but eliminating like the diagonal line where x equals y. Let's take the partial. So derivative of f with respect to y is going to be, now here we do need the quotient rule. So the derivative of the numerator, which is actually just 1 times the denominator minus the numerator times the derivative of the denominator, which is 1, okay, over the denominator squared. So we get negative 2x over y minus x squared. And we can see that that partial is continuous, again, when x is not equal to y. And so our conclusion is that the IVP would have a unique solution as long as the x and y that are given are not equal to each other. So going back to our original question, we can actually just answer both of these right away. First one, yes, 3 is not equal to 7. Second one, no, 6 is equal to 6. I do need to make a follow-up comment here. Part B, we answered no. That does not mean that there's no solution. It just means that it doesn't have a unique solution. So it could mean that there are just multiple solutions that intersect there. It also could mean there are no solutions.